The squeeze limit is one of the most important tools in calculating limits, especially when those limits include trigonometric functions. Let's examine again the graph of this function f of x equals cosine of 1 over x. And if you recall, I discussed this in a previous video, doesn't matter how close you get to 0, the graph oscillates even more widely between -1 and 1, and therefore there's no one value that the graph approaches, because you can find, doesn't matter how close you go to 0, you can always find something very close to -1 and something very close to 1, which are therefore very far from each other. So the limit when x approaches 1, recall that the limit when x approaches 0 of f of x does not exist. Recall that. We discussed this in a previous video. Now, how could we possibly fix this? And this is how the squeeze limit theorem works. We're going to try and squeeze this -1 up and this 1 down to sort of force them to go into 0. It's not something we are always trying to do, but sometimes you can see a limit that's given to us as being a squeeze of this type. So let's take as an example, let's look at this function right there, which is x squared cosine 1 over x. So very similar. The difference is that we're multiplying this x squared in front now. The idea is that, okay, isn't it true that cosine of anything is between 1 and -1? That's always true. So if you multiply each of those inequalities by x squared, so basically imagine multiplying each of those by x squared, you get minus x squared between cosine, or x squared cosine 1 over x and x squared. So that means now this new function that we use is between minus x squared and x squared. So if you were to graph these guys, x squared is like this, and then minus x squared is like this. So the green function keeps trying to oscillate, right? Keeps trying to oscillate, but as it approaches, it's forced in between the other blue ones, right? It keeps trying to oscillate, but in fact, it can't oscillate above any of the two parabolas, above or below, right? It's got to stay between them. So because this guy, x squared, it tends to 0 when we go to 0, the limit equals 0, and the other guy, the minus x squared, also goes to 0, so they both tend to the same limit. The green function, right, the x squared cosine 1 over x, has no choice but to also go to 0, because there's nowhere else for it to go other than to stay in between minus x squared and x squared. There's a more formal way to prove this, but so far this is, I think, a clear idea. I'll show you later a graphical animation of this, but you can formally state the squeeze limit theorem as such. You have f of x and g of x, which are the outer functions that are bounding g. So if I want to make another graphic, you have some point A, x near A, so let's say this is A, and you have these two graphs, let's say F right here, and then another, and the most important thing is that F and G coincide near A, and that H is, sorry, that's not true, right? Let me correct that. G, so I have here, H is the top one. So H is the top one, F is the bottom one. And now do green to do G. G has to stay between F and H, but all that matters is what happens near A, so maybe all the way over there, H is G is super awkward, but as long as we're close enough, it's forced to stay between F and h, so this is y equals g of x. And even on that other side, right, does that, and maybe like it escapes over there too, but as long as you're close enough, you're forced to stay between f and h. So if you look into this, then this property is satisfied. G is between f and h. The other condition that you need to check is that the true limits are equal. So this is the other condition. The limit of f and the limit of h equals L. They both equal L. So what does that mean for us? That, as a conclusion, forces the limit of g, of the green one, to also be L. So L for us will be the y coordinate of this. We're going to do it in black. So because h goes to L, and because f goes to L, and because g is between these two, g has no other choice but to go to L as well. Okay? So let's see this example. Look at x sine 1 over x, very similar to the previous one. Let's easily and formally prove that the limit of this guy exists. So let's see that. So we know that sine of 1 over x is always between 1 and minus 1. Doesn't matter what x is, as long as 1 over x is well defined, meaning x is not equal to 0. Right? So if you multiply this by x as well, you get minus x sine 1 over x, multiply x on each of the three parts of this inequality. It's actually two inequalities, but okay. Now, so this is this condition, we're good. Now we know that limit x when x goes to 0, that's a linear, easy linear function, that's 0. Limit minus x when x goes to 0 equals 0. So that means that by the Squeeze theorem, it is also true that the limit as x goes to 0 equals 0. The two limits are equal, and this guy is between the two, so that forces it to also have that limit. Okay, so this is a very good standard way on how to prove that a limit exists using the Squeeze theorem. Another is to do this. This is B, right? Let's take a look at B. B is saying that you don't know anything about f this time. We don't know the formula for f, so it's an unknown function, but we do know that it's between these two guys. So we know that the limit of 2 when x goes to 2, right? And I'm using this a value there. This equals to 2, of course. So the function 2 is this horizontal line over there. Okay. Now the other limit that I find is 2x squared minus 6. So the limit of 2x squared minus 6. So this is a quadratic polynomial function, right? Polynomial quadratic function. And I can just use direct substitution for this limit. So that's 2 times 2 squared minus 6. So that's 2 times 4 minus 6. That's 8 minus 6. That's also 2. So this is a parabola, kind of like a concave down parabola like that. It's concave up rather, right? Parabola. I don't quite care whether this is above or below or the shape of the parabola precisely, but near 2, right, near 2, let's say the parabola is like this. It is not, but let's pretend, right? Because, so this is y equal to 2x squared minus 6. Because the function in the middle, and this is going to be my green function, is forced to be between these two, doesn't matter what it looks like. Doesn't matter what it looks like. It doesn't matter how it oscillates like I did. This graph is very, very weird for a function, but even if it's that weird, because it's forced to be between these two, and these two have the same limit when x approaches 2, the squeeze theorem is going to tell me that the limit when x goes to 2 of f of x also equals to 2. So just to make sure that neither of you is confused, this 2 is going there, and the 2 at the bottom there is coming from this. Right? There's these 2's. They're the x value that we're approaching, and the y value is this 2 right there. Let me outline for you graphically how the squeeze theorem works. So you have this original green function that we had before, and these are the two parabolas that we're gonna squeeze our original graph between. So I'll hide them for now. And because this green function is implemented statically, I'll replace it by another one that's not static, which I believe is this one. This one is supposed to change with t. So t is a slider that I'll change, that I use to change how the function squeezes. And this is going to be q and r are the two functions that are going to squeeze. So they're going to become g and h. So they're going to become the two parabolas. So as t grows, these lines, they get closer and closer to 0, to the parabolas, and they squeeze, they force the oscillation to stop. It still happens close enough, and if you zoom in, if you really zoom in, you can still see some oscillation. But the function, the orange function in between, is never allowed to oscillate too much because the two parabolas are forcing it to stay where it is. So if I allow it to animate, you're going to see what I'm talking about there. You have the parabolas, the original function, as soon as these become lines, and then as they approach parabolas, the parabolas that we had, right, the black ones, if you remember, right, they're approaching the black ones. We're squeezing them further and further and forcing the oscillation to stop and forcing the limit of the orange function to be 0 as well.